Now that we've talked about matter and had a brief introduction into the periodic table, let's talk a little bit more about elements and about atoms. I won't normally talk this much about history, but this particular topic, our understanding of the atom, really, I think it's helpful for us to have some context in here. So that's why I am developing our topic this way. So, of course, we talked about how some elements had been known from antiquity, and some of those were popular popular materials like gold and silver right here, copper, iron, sulfur over here, carbon, phosphorus. But many of the elements were not discovered until quite a bit later. And so people knew them based on their properties, that they were different from all of the other materials that you could test, and you couldn't break them down, right? That became our part of our definition of what an element is. And we talked about Antoine Lavoisier in our previous lecture as well, and he actually coined the term element in 1777. So when we talk about atoms, this is actually a really ancient term. It was coined by the Greek philosopher Democritus in 400 BC. So this idea was that there is some irreducible form of matter, that atom means uncuttable or undividable, that you can't break it down into any other pieces without it losing its identity. And so, of course, he didn't understand matter the same way that we do, but the term has been one that has been kicking around for a long time, and we continue to use it now. So when we look at our understanding of the atom, of course, we just saw that it was in the mid to late 1700s that Lavoisier was revitalizing this idea of the scientific process. So John Dalton continued this practice of science, and in 1803 he proposed that elements exist in tiny particles, and in 1808 he actually published the first atomic theory and he based this work on his research, which was on gases. So when he was doing his research, he would react gases together. He took careful mass measurements, and he also looked at what the mass ratios were of how things reacted. So he came up with 4 principles in his atomic theory. The first one was that elements each have their own type of atom and that they're different from every other one. And he noted that these were indestructible and unable to be divided into anything else. So the second one was that all atoms of an element are identical. And we'll see that that isn't 100% true in a little while, but it was still pretty firm for his time, and absolutely true for the ability of his equipment to measure the differences. Okay, so all atoms of an element are identical, and each element's atoms are distinct from any other element and their atoms. Okay, the next one was that atoms combine in simple whole number ratios to form compounds. And finally, that atoms are not changed, created, or destroyed when they undergo chemical reactions. They are just rearranged. So John Dalton's atomic theory was a great start, but it didn't take too long before people realized that there were actually some smaller particles besides for atoms, and some of which actually came from inside of atoms. And so even though we're not going to talk very much about radioactivity and nuclear chemistry right now, we will actually talk about it quite a bit later. So I'm going to give you a little bit of a background here, understanding how we figured out about subatomic particles and whatnot. So the next guy that we need to talk about is J.J. Thompson. And J.J. Thompson is credited with the discovery of electrons. This is 1897. So yeah, I know we've had a big jump between John Dalton and J.J. Thompson, but that's just how it is, right? We're sticking to a certain set of what kind of science topics we're going to discuss. J.J. Thompson was doing an experiment with something that he called a cathode ray tube. So this cathode ray tube was effectively a glass vacuum tube, and he had an anode and a cathode, and these were hooked up to some kind of a battery. And what he did was he also pumped out the air from inside the cathode ray tube. So this is just sort of the standard one. Well, no, I guess these have electrically charged plates on all of them. So what he noticed was that once he had pumped out all the air, but he charged up this battery, if he put some kind of a phosphorescent coating on the inside of this other end of the tube, he saw a little bright spot at some point that was right in line with where his electrodes connected up with this. So he had pumped out the air, remember? But he realized that there had to be some kind of material that was a fairly high energy particle that was inside his cathode ray tube. So he decided to test it, and one of the things he could think of to do was he used some magnets. And so he set up some magnets and realized that if he put the magnets in different places, he could get this cathode ray, that he called it, to bend. And depending on where he put them, the cathode ray would bend in different places. And in this case, you see that they are balancing each other out, and this cathode ray just goes straight on through. So what he could understand from that was this cathode ray has a charge. He knows that a charged particle that's moving sets up a magnetic field, and so it's going to be deflected by another magnet. And here he actually is just using these electrically charged plates, and so he's exposing this ray to an electrical field. So he notices that this is both a charged particle that is moving, and he can deflect it also with an electrically charged area. So he went ahead and concluded that you had this electron, this negatively charged particle, that was being emitted. Well, what was it emitting from? It had to be emitted from his cathode or his anode. So from the inside of an atom. So he called this beam initially a cathode ray. and eventually cathode rays became understood as electrons. He also measured the charge to mass ratio, and it always stayed the same. So he knew it was the same particle every single time, the same kind of particle. He just had one kind of particle. So this is the first of our charged particles, or our subatomic particles, that's discovered. But meanwhile, we also have some research that's going on that also relates to the inside of the atom. And this is being done by a French scientist, Henri Becquerel. He was doing research about the same time, and in 1896, he discovered that he was working with a mineral called pitchblende, and he discovered that it emitted some X-rays, which had also just been discovered quite recently. He discovered it pretty much by accident. He had in his drawer some photographic film, and he accidentally exposed it because there were some rocks of this pitchblende in a nearby drawer. Here's the image. It doesn't look very exciting, but the point was that he had not expected to find any energy coming off of these rocks. So he realized that these X-rays had to be emitted from the rocks. It wasn't like they had been charged up by the sun and then were glowing the way we would think of as a like a glow-in-the-dark star or something on one ceiling. And so this research was continued by Marie and Pierre Curie, who extracted some new elements from the pitchblende. They discovered polonium and radium, and I think also francium, over time anyway. And Marie Curie coined the term radioactivity to describe this energy being released from inside of the atom. And she realized that these X-rays were being emitted from the nucleus, from inside the atom. So the three of them shared the Nobel Prize. I forget what year, but early 1900s. So with all this talk about atoms and nuclei, you probably would not be surprised to learn that Thompson decided that based on what he had discovered and also understanding this emission of radioactivity from the nucleus, that the atom must be something like this positive and negative charged kind of mush. He called it the plum pudding model, but we are not really familiar with a British plum pudding, so it might be easier to think about it as, I don't know, maybe a chocolate chip cookie model, where you have a solid mass where interspersed in this mass, like the chocolate chips in a chocolate chip cookie or the raisins in a plum pudding, would be all of the little charged bits that are inside the atom. So this was his plum pudding model. And J.J. Thompson, he was a very reputable scientist, and so most people accepted that this probably was going to work. And we have coming up, though, Ernest Rutherford, who joined the same university. They were all at Cambridge, and he had come from New Zealand to England, and he had already made several additional discoveries that were related to the Curie's and Becquerel's research, which was that atoms also release not just X-rays, but positively charged particles that he called alpha particles. That's the Greek letter alpha. And negatively charged particles that he called beta particles. And I think they are called alpha and beta because he found the alpha ones first and the beta ones second. And alpha is the first letter in the Greek alphabet, and beta is the second one. So there wasn't anything super fancy about it. And he also called the gamma rays, which had no mass. These positively charged alpha particles were large, relatively speaking. They were about the same mass as a helium atom, based on charge to mass ratios and so on. And these negatively charged beta particles had the same charge to mass ratio as an electron. And so he concluded after a while that they must just be electrons. And that's true. Beta particles are electrons. So Ernest Rutherford decided to test J.J. Thompson's plum pudding model. He said, look, if I have these large alpha particles and I shoot them into a bunch of material that looks like this, then all of these little negatively charged electrons that are scattered around here should deflect my alpha particle because, well, they probably will attract the alpha particle, right? So if my alpha particle is coming through here, then it's probably going to be pulled toward those negatively charged particles, and it'll be slightly deflected, and maybe it'll bounce back and forth and who knows what. But it should be deflected, and it might also be deflected the opposite way by these positively charged particles, right? If I have one coming in like this, it's probably going to be repelled by that positively charged particle that happens to be inside this. So he set up, which is an experiment that is famously called the gold foil experiment. Rutherford had his students set up this experiment. He had in this block an emitter of those alpha particles that we were just talking about. And he set up a thin piece of gold foil. So think like a piece of aluminum foil only made out of gold. And then a big fluorescent screen that was almost completely around in a circle. So his idea was that he would be able to have his students see the slight deflection that he was expecting as these alpha particles were slightly deflected by the positive charge of the electrons that presumably were scattered around through this positive area of mass. So this would have had to have been done in complete darkness so the students could see where the actual location of the bright spots were. So the experiment had some pretty unexpected results. The vast majority of the beam of light of the alpha particles that were emitted just went straight through with no deflection. And then occasionally you'd have one that was somewhat deflected, quite a bit, and then you actually would have some that were almost entirely deflected all the way back toward the source of the alpha emitter. So rather than this diffuse path of positive charge through which the alpha particle would be deflected by the negative electrons, what Rutherford proposed as far as a modified model here is that we would get instead that the mass of the nucleus is where all of the positive charge is, and it's a large, heavy mass with a mostly empty space out here with occasional electrons from here and there. And rather than being deflected by these electrons, mostly they just pass right through that negative charge, and occasionally the alpha particle will be lined up so that it is deflected either straight back or at a fairly large angle from that massive nucleus. So through these experiments, not only did Ernest Rutherford come up with a new model for the atom, which was the one that we just saw, that we have a hard, positively charged, who knows what it is, right? Here's the nucleus. Its mass is high, relatively speaking, and it's positively charged. And then we have electrons scattered around outside it. So the nucleus is small and heavy. And positive. And the electrons are scattered outside. And although this is not exactly identical to our modern model, it is very, very similar to our modern model for the atom, which we'll talk more about in a little while. But the other thing that really was important that came from Rutherford's research was that they were able to identify 2 additional subatomic particles. So we have a total of 3 subatomic particles. We have the electron, and we use E, usually with a minus sign here to represent it. Proton, and we use a P, and then neutron, and we use an N. And protons have a positive charge, electrons have a negative charge, and neutrons have no charge. These all also have a well-established masses. I'm going to copy them in. So these are the specific masses in kilograms for the neutron, the proton, and the electron. You don't need to memorize these. The other way that we usually talk about these is that, well, I usually try and just look at how big they are. So notice that these are approximately 1,000 times bigger than the mass of an electron, or more massive than an electron, right? So we have these 3 important subatomic particles. The other thing that I want to follow up with was John Dalton's comment about atoms, that they all are identical. And this is mostly true. So each atom has a set number, or excuse me, let me back up. Each element has a set number of protons in its atoms. And it's always the same. This is called the atomic number. And it's often given the symbol of a capital Z. So when we look at the periodic table, the number, let's switch over. Over each element, the number over each element, that is the atomic number. That is the number of protons in the nucleus of each atom. And notice that when we were at that periodic table, each element has its own individual number. So if you have 22 protons in the nucleus, that means that the element is titanium. But if instead it has 23, that element is vanadium. A neutral atom has the same number of protons as electrons. The charge of a proton is equal to the charge of an electron, and so if you want to have something that doesn't have a net charge, then you're going to have the same number of protons and electrons. And then atoms also have neutrons. And the mass of the neutron is almost exactly the same as the mass of the proton. Notice that it's slightly higher, right? 1.6749 times 10 to the minus 27 kilograms versus 1.6726 times 10 to the minus 27 kilograms. So the protons and the neutrons together make up most of the mass of the atom. And if we add these two numbers together, this is called the mass number of the atom. And it is given the capital letter A as its symbol. So although each element has one specific atomic number, the atoms of that element can actually have a variety of different neutrons. And these are called isotopes. And we have two more scientists that I'll just mention really quick. We have Frederick Soddy, who is the one who realized that there are isotopes and coined this term. And then this was confirmed by Francis Austin. Soddy was another of Rutherford's students. I actually don't remember if Austin was working with him or not. But Austin invented the precursor of the mass spectrometer that we use for determining masses of different atoms. And they also got Nobel Prizes. So he got the 1921 Nobel, and Austin got the 1922. Pretty cool stuff. So if we were going to talk about these different isotopes, we should probably take a second to put this all together and notice that we have a specific isotope notation. That each element has an elemental symbol, which I'm just using X here. There is no element X, which is on the periodic table. And then the mass number will be up here on the upper left, and the atomic number will be up down here on the bottom left. And this would be the complete isotope notation for any particular element. So if we go back over to the periodic table here, and we look at carbon, they have right here on the second page for carbon, they have put carbon with its atomic number right here, 6. And if we go down and we look at the isotopes that are present, we can find that over here under the carbon isotope information. And you will see that there are two naturally occurring isotopes of carbon, carbon-12 and carbon-13. And because they already have that carbon has its atomic number 6 down here, they haven't bothered to put the 6 down here on the bottom left. They just have the mass number up here, carbon-12 and carbon-13. So if we look at those two, carbon-12 and carbon-13, they both have the atomic number of 6, which they have to have. So how many protons does carbon have? Hopefully you remember that this number tells us the number of protons. So carbon has 6 protons, and the same is true for both of its naturally occurring isotopes. So how many neutrons does it have? Do you remember that we said that the mass number, A, was equal to the number of neutrons plus the number of protons? So if we look at this mass number, which is 12, that's going to be the number of neutrons plus 6 for carbon. So for the carbon-12 isotope, it has 6 protons, 6 neutrons, and if it's neutral, 6 electrons. Over here for carbon-13, what's the difference between carbon-13 and carbon-12? It's not the atomic number. They both have 6 protons. It is the number of neutrons. So carbon-13 has 6 protons, 7 neutrons, and 6 electrons. So I'm going to stop here, and in the next video we'll talk about calculating the average mass of elements on the periodic table, and then we'll go from there.